Hello and welcome back to Day 3 of the FlexSim Core training course. Today we will begin by talking about a very powerful and useful feature within the software known as task sequences. Task sequences are the mechanism by which mobile resources like operators and vehicles are given instructions to carry out tasks, such as to load, travel, and unload. Mobile resources are called task executors in the software because they, as the name suggests, execute task sequences. A task is a single instruction or action to be performed by a task executor object. An example of a task is to travel to another object or to load a flow item. A task sequence is a series of tasks to be performed in a sequence. Task sequences are assigned to task executors, such as operators or transporters, and each task executor could have a queue of task sequences that have been dispatched to them at some earlier point and have not been completed yet. When a task executor completes a task sequence, it will immediately begin executing the next task sequence in its queue. So let's take a look at how and when task sequences are created automatically by the 3D objects in a model. Do you remember looking at this colorful flowchart on day 1? It maps out the sequence of events occurring on a 3D processor object, starting from when a flow item first enters the object to when a flow item leaves the object. The right half of this slide shows fields in the Properties window for a processor object. If we check any of these three checkboxes to use operator for setup, or use operator for process, or to use a transport to carry the flow item to the downstream object, then the processor's behavior will create a task sequence. The purple diamond decision blocks in the flowchart show the points when the associated task sequences will be created and dispatched if designated by the corresponding checkbox in the Properties window. The Pick Operator field, this one here, and the field here next to the Use Transport field is where we define which object, either a task executor or a dispatcher, we want the task sequence dispatched to. As a reminder, the default expression for both this field and the Pick Operator field refers to the object that is connected to this current processor object's center port number 1. Now, the two attributes of priority and preemption are attributes of every task sequence and can be defined by us here and here on this property page as well. Both dispatcher objects and task executor objects have a task sequence queue in their data structure that determines the order in which queued requests will be handled. Every task sequence is assigned a priority value that is used to sort the task sequence in the task sequence queue. A higher value for the priority attribute indicates a higher priority and will place the task sequence at the top of the queue. The preemption attribute's value indicates one of 4 predefined preempting rules, ranging from a value of 0, which indicates no preempting is allowed, up to a value 3, which specifies that preempting is allowed, and when preemption occurs, all other task sequences on the task executor will be aborted and destroyed. Task sequences that are allowed to preempt will interrupt another lower priority task sequence that happens to be in progress by the targeted task executor. Okay, we're going to take a look at this example model that I've built in the software to see some of the task sequences that are generated automatically by the 3D objects. In this example model, a single operator, which is our task executor object, will be given task sequences for carrying flow items from the queue to the first processor, and then from processor to processor, and finally to the sink, as well as be given task sequences to be utilized during the process time at each of the 3 processors. So let's first look at the properties of some of the objects to see where we are going to be requesting an operator. First, the queue. On the Flow tab, we have checked the box to use transporter, use transport, and the reference to which transport task executor we want to use. It's the default current.centerObject1. So it's going to dispatch the task sequence to carry the flow item to the first processor to whatever object is connected to the first center port of this current queue object. Let's take a look at one of the processors. All of the processors have the same properties. On the processor tab, there's no setup time and no operator used for setup. But there is a process time of 10, and this box here is checked to use operator for process, which operator is defined on the pick operator field line, and it's the default again. So this will create a task sequence, populate it with some tasks to travel over and be utilized during the process time, and then be freed up. And it'll send it to, once again, the object connected to the first center port of this current processor object. And also on the Flow tab is a use transport. All the processor objects have the same information on them, and notice how all the center ports of the processors and the queues are connected to this operator. Alright, let's run the model to generate some task sequences. Now, if we stop the model after the operator has performed some tasks here, I'm going to try to stop it when the operator is in the middle of performing a task and has some other tasks queued up. Okay, I'm stopping it right now, and I want to look in the object data tree of the operator. I already have the model tree open here and have expanded the data tree for the operator. So because the operator is in the middle of executing a task sequence, there'll be one task sequence in the active task sequence variable node of the operator, and sure enough there is. It's a task sequence named TS16, and if any other task sequences have been dispatched to this operator, they will be queued up in this variable node called task sequence queue. Although we rarely find need to spend time doing anything with the nodes in this tree view, I think it's helpful to know that it exists and that these task sequences are represented by actual nodes in the tree. Notice that each task sequence has a priority value and a preempt value. And also notice it tells us what is the current task in the task sequence. If we click on this plus sign here and expand the task sequence node, we can see all the tasks that are in this task sequence. So this task sequence here is composed of 4 tasks. Let's look at this queued up task. It's composed of 5 tasks. You can learn a little bit about what is going on in the task sequence. This first task, for instance, is to travel to processor 10 and then load the box that's in processor 10. Okay, let's go back to the model. Have you noticed that the operator is running around a lot? Because the task sequences are created at different moments in time, the operator appears to handle tasks erratically. But it's perfectly in order with the timing of when the object events dispatch their task sequences. Sometimes this behavior is fine, but sometimes it's not at all what we want, and we need to either modify the dispatch task sequence or create our own custom task sequence, which we will do in a bit. When task sequences are built automatically by the behavior of the 3D objects, as in this model, the task sequences are first created Then it's filled with a number of tasks, and then dispatched as a complete task sequence to the executor, or in some cases a dispatcher. Next, we're going to look at how to build custom task sequences using process flow activities, where we will create a task sequence and dispatch the task sequence before adding tasks. And the tasks we add to the task sequence will happen over time, one after the other, as previous tasks are completed. So that's where we're headed. One of the great applications of process flow is the ability to construct our own task sequences exactly when and how we want. We're now going to look at how to create and dispatch custom task sequences using a process flow. In the process flow library, there's a category called task sequences, made up of these activities you see here: create task sequence, finish task sequence, travel, and travel is broken out into three types of travel: travel to object, travel to location, and AGV travel. Load, unload, delay. A custom task, which opens you up to a whole nother grouping of tasks like start an animation or change a visual. And then this last activity called dispatch task sequence. Most of the task sequence related activities are pretty self-explanatory based on the name of the activity itself, but the create and finish task sequence activities require a little more explanation. The create task sequence activity will create an empty task sequence and optionally dispatch it to a task executor. By default, this activity is configured to create a task sequence that uses a wait state. This means that once the task executor begins executing the task sequence, it will not move on to other task sequences until it is explicitly given a finished task. For this reason, this activity is meant to be paired with the finish task sequence activity, which is used to assign the finished task. You can see here that in the create task sequence activity, you're asked to define or specify a label on the token that will track this. The default is token.taskSequence. We usually leave that as it is, and then in the finish task sequence it references that label to match them up. By using a wait state and a finished task sequence activity, we can more easily use task sequences from both 3D objects and from process flow. It also creates a natural acquire-release mechanism that can sometimes replace using acquire-release resource activities. We can now use the task executor / dispatcher box to select the task executor or dispatcher we want to assign the task sequence to. If we want to create a task sequence but not dispatch it yet, then we leave this field set to none, and we uncheck the dispatch and wait box. Once we know who to dispatch the task sequence to, we'll need to use a dispatch TS dispatch task sequence activity to assign the task sequence to a task executor later in the process flow. The majority of the time we will go ahead and specify the task executor or dispatcher up front and let this create task sequence activity dispatch the task sequence immediately. The task executor dispatcher can be assigned explicitly with the sampler or found via an expression such as a label reference. Notice the priority and preemption fields available to specify these attributes of the task sequence that gets created. The wait for finish state defines the state to go into when the task executor is waiting for another task to be added to its task sequence. If there are delays that don't put the task executor into a state natively, then this is the reporting state the task executor will be in until another task puts it into a state. This will count towards the default utilization calculation on the dashboard, so it's important for meaningful utilization reports. Let's revisit that example model again. Instead of having the operator handle tasks in the order the tasks are generated in, what if the behavior we are really looking for is to have the operator follow the same flow item through every step of the process? Well, the easiest way to do this is to create a process flow that interacts with the events of the 3D objects in the model. The process flow will be kicked off with an event-driven source that's tied to the on-entry event of the queue. The process flow consists of an initial create task sequence, create TS activity, and then a number of tasks to load, travel, unload, and then wait for the processors to finish processing the part before repeating similar tasks, and then is wrapped up with a finish task sequence, finish TS activity, and a sync for the token. So let's take a look at this actual model in the software. Here it is. We'll reset, run. First box comes in, operator carries it and stays with that box throughout the process, carrying it and processing it until it finally gets carried to the sink. Look at the process flow on the right. There's a token in there for each of the flow items that have entered the model, or entered the queue. And they line up here. A task sequence is created for them, and then it waits. They wait their turn. Okay, that's what it looks like. Now let's see how it was built. Stop the model, reset. It all starts with this event-triggered source right here. And it is this object in the library, event-triggered source. Let me drag a new one out here. This event-triggered source has a little red exclamation point to the right of it. If you mouse over, you get the sampler button. So we'd use that to sample this queue, and then choose the on-entry event, and it gets filled out for you automatically. And that's what's been done up here with this object. So let me delete that. And if we look at it, it's Q17, the on-entry event, and then that token that gets created every time a flow item enters the queue goes into this activity here where a task sequence is created for it. And as mentioned, down at the bottom, the finish TS activity is tied to that same label on the token, token.taskSequence. Notice how there's no connections between the queue and the processor or between any of the objects after that. All the travel is handled with the process flow. Okay, so after the token has created the task sequence and dispatched it to the operator, the token waits until the operator accepts the task sequence, making it the active task sequence for the operator, and then it proceeds forward to the next task, which is a travel task, to travel to the queue, and then a load task to load the flow item from the queue, then travel to the first processor and unload the flow item to the first processor, and then wait. So this is a wait for event activity, and it's waiting for the processor's release event when the flow item gets released. And then that starts the next series of activities to travel to that processor, load, travel, unload, and this is repeated for each of the next processors. And then finally the flow item is carried to the sink, and the task sequence is finished, so the operator is then able to accept another task sequence as its active task. Before I turn you loose to build your own task sequence model, I want to introduce to you the batch activity. It is a very useful activity which you'll find many uses for as a modeler. It has a tremendous amount of flexibility in its design and intended uses, which can make it a little difficult to explain. It's easiest to think of it as an activity which simply collects a number of tokens over time up to a predetermined batch quantity, and then releases all the tokens as a batch. However, it's much more flexible than that. Generally speaking, the batch activity collects a specified number of incoming tokens, sorting them into separate batching groups even if needs be, and then releasing another specified number of tokens. Sometimes the number of tokens released is the same as the number of tokens collected, sometimes it is less, and sometimes it can even be more than the number collected. Well, to better understand this batch activity, let's play around with it a little bit in the software itself. Okay, create a process flow, general process flow, and that's all we're going to work with, so I'm going to close the 3D model view. We'll begin with an enter arrival source, and then let's just click and drag and create a delay task. I like using delay tasks when I'm experimenting with new activities because it holds the token long enough for me to see what's going on. Let's have our enter arrival time be a constant value of 5 seconds, and then delay them here in this block for 2 seconds, and then we'll run them through a batch activity, and that's this one here. In the library, it's under the basic group right here. We'll go with the default. It has a batch quantity of 2. It's using number of tokens as the quantifier, and number of tokens to release is 1, and no grouping, and no max wait timer, and no max idle timer. We'll go with that default. Good starting place, just see what that's going to do. And then let's put the tokens in a delay block again and delay them here for quite a while. Let's delay them for 100 seconds so that we have time to click on them and look at labels and stuff. And then we'll route to a sync. Okay, let's start the model running and stop. I should probably slow this down to about let's go with close to 1. Okay, I didn't even see what happened. It happened so fast, so let's start over again. Reset run. There's our first flow item. Spends 2 seconds in there. Comes in here to the batch activity, and it waits for another one to come, which it did. And so then one was released. This one represents the batch. Another batch is being built up. And we have 2 batches that have entered our final delay block. And if we click on the batch and, well, right click, show batch statistics, that might be useful to help you understand this, how many tokens have entered and exited, and batch quantities and batches released. Has a lot of information that might be useful. I'll set that over here. If I click on right where the batch was being built, it'll give me information about it, but I was too late. Let's click here. Okay, there's the one token ID in there. Waits for the next one. Alright, so you get the idea of that. Stop, reset. Now, I want to, well, let's do one thing before I start adding labels. Let's have the number of tokens to release be the same number as the batch. Now I could write 2 in there, but if I don't know what the batch quantity is, a good option in this field is the batch quantity itself. Okay, so we should see 2 tokens come in and then 2 leave. There's the next second one of the batch entered, and here's the 2 exact same tokens that entered the batch, left the batch, and any labels on them would be kept. Okay, stop. Now I'm going to add a label to the flow item. I keep saying flow item, token. Okay, assign labels, and let's use that example of weight. Add a weight label to these tokens, how much they weigh. Let's use a distribution. To make it easier to track what's going on rather than a straight uniform distribution, I'm going to use a discrete uniform so we get the numbers 1, 2, 3, 4 up to 10. And we can think of those as kilograms or pounds or whatever. Okay, each token is going to be assigned a number 1 through 10, uniformly distributed. Okay, now for the batch. Let's have the quantifier, instead of being number of tokens, let's have it be a token label, and there's our label weight. And let's say our batch quantity is 20 kilograms. And what is our, we still have tokens to release being whatever the batch quantity is. Let's change that to 1. Let's release one thing representing the batch. So this example might be a box or something that we don't want to pack with more than 20 kilograms of items. And then the one thing that leaves will represent the box, and the things that come in will represent the products put in the box. Okay, let's start the model running again. Okay, there's our first item. Stop it. How much does it weigh? Click on it. Look at its weight over here. Has a weight of 1 kilogram in our way of thinking here. Continue running. Okay, so it's 1 kilogram of a 20 kilogram batch. The next one must have had a weight of 1 as well. And the third one had a weight of 1. Interesting. Here's the fourth token to enter, and it had a weight of 9 because it brought it up to 12 kilograms out of 20. Fourth one was brought it to 19, and then let's stop. Okay, so the last token in made it hit our 20 mark or above. And what's its weight? Its weight is 1. Okay, 1 whatever. So why did it do that? Well, let's look at our settings on the batch activity. And this overflow field comes into play now. This is where we choose how to handle overflow or excess collected quantity for our batches. And that last item to enter, I'm not sure what it was because I didn't stop the model, but it took us over 20. And this particular overflow rule says don't divide that last token that comes in. Instead, just wipe away the excess. Release the excess. Now, let's choose one of the divide options, the last two, either hold excess quantity or destroy excess quantity. Let's destroy excess quantity and see what happens. Now we've got label aggregation. I think what might be interesting is set this up so you understand it. The from label, let's have it be whatever the weight label of the token is. And the to label, that means the label we want to write on the one token we're releasing. Go ahead and call it weight as well. And then this aggregation column has several options in here, and hopefully this will start to make sense. As I use this option, the sum, I want to take the sum of the from labels, and that becomes the value of the to label on the one token that gets released, because that one there. Let's see what we get. Reset, run. Because we're repeating random streams, we should get the same thing again. The first token that comes in is a weight of 1 kilogram. Second one is 1, taking it up to 2. Third one is 1. The next one is 9, if I remember right, taking it to 12 of 20 kilograms. And then I'm going to stop the model when we get this next one in here so we can look at some things. Click on it. What's its weight value? It has a weight of 7. Okay. And right now we're at 12. Oh, okay, that's going to take it to the 19 we saw. Let's keep running. And stop it when this next one enters. Stop. This token has a weight of 5. Okay, that's going to take us up to 24. We're going to have overflow. Well, remember our overflow, we said we want to destroy the excess quantity, but we want to record the sum of the weight. So I would expect to see the weight label be 20. Let's see if it is. Run. Stop. Now it has a weight label of exactly 20. Destroyed the the excess, so the batch counter is cleared out and waiting for a new batch. I probably should have left it the way it was so you can see what happens if we don't destroy excess quantity. Let's choose this default. Go back to this default one of do not divide, release the excess. Okay, so now we should see it go up to 24 on the last one. Here's the fifth one, and the sixth token enter is going to take us over the top. Stop it, and the label weight is 24. It released the excess with the released item, so it wrote exactly what there was to release. Okay, now let's look at some of the others. I think if we look at least one more, you'll get the idea of what these overflow rules are. Let's do not divide, release partial. We're going to release partial. Start one, second flow item, third flow item, fourth flow item, fifth flow item, sixth flow item. Stop. We see the weight is 19. It released it as a partial batch. The last one that came in, remember, had a value of 5, and it starts a new batch, and it released the first batch. Says go on ahead as a partial batch because I'm going to exceed or overflow. Each of these will have a use somewhere in your modeling career if you do much modeling, so it's probably a good idea to go through these. How about hold excess quantity? First token, second token, same as before. Fourth token, fifth token will take it to 19. And let's see what happens with that next token that overflows. Okay, overflow. Click on this released item. It has a weight label of 20. And 4 kilograms are left in this batch activity to help start the new batch, populate the new batch. Kind of interesting how that works, isn't it? Okay, now one more thing I want to show you. I want to go back to using number of tokens, have the batch quantity be 4, but use a max wait timer. When I check the use max wait timer box, it brings up 3 fields. A start criteria field. It's the criteria for when the max wait timer will start. After it's collected at least one part, then start the max wait timer. How long do you want the timer to last? Let's say last for, they're coming in about every 5 seconds. If we don't last for at least 20 seconds, or let's last for 15 seconds. Wait for 15 seconds. Max wait timer after having collected the first part, and see if that's long enough to collect all 4 of the batch quantity. Now on wait timer fire, the default option here does release the batch, although you don't need to release the batch. That's not the sole purpose of the max wait timer. It's just a trigger in its simplest form, purest form. It does 2 things by default. It sets a label on the token called failed and sets it to a value of 1, and then it releases the batch. This is when the wait timer fires, max wait timer, and it releases the batch to destination 1. That's referring to a connector. You can refer to the connector by rank or name, or the activity the token will end up going to. And then there's this box here called failed. You check to fail the batch. This will cause all of the tokens in the batch to be released and will not evaluate the number of tokens field up there to release or perform the mathematical operations on the token labels. So we have a couple different options. I told you this activity, it's technical. It was designed over time as new users would come up with a different scenario that they wanted to capture that was related to batching. And so don't be too concerned about all the options until you need them. Start off using it just as so many parts come in and so many parts leave. Okay, but right now it's going to release the batch to connector 1, which is the sync. Okay, or excuse me, the delay object. Alright, reset, run. Remember, we're waiting to get 4 things for our batch. There's 1 of 4 things, 2 of 4 things. Our timer has started when that first one enters. I'm not sure where we're at on the 15-second mark. Let's see if it waits for another one or if it releases early. It looks like it did fail and released early. And that last one that came in was the start of a new batch. It was hard to see the timing, but that's what happened. Now, the other thing you need to be aware of, and I think just by introducing you to these ideas, that hopefully somewhere in the back of your mind you'll remember that the batch activity can do quite a bit and investigate it further when the need arises. But it has this other option to use a max idle timer, and this allows you to define, as the pop-up there shows, a max idle timer that will fire if the batch does not receive new tokens within a certain time. So this is, once again, has a start criteria field, and usually you just leave that as it must have started collecting something. Collected must be greater than 0. Then you say how long to wait between each collected token, the maximum amount of time to wait, and then what to do if that idle timer ever fires, and the default is to set a label and release the batch. Okay, let's reset the model, and then I want to demonstrate the group by feature of the batch activity. To this point, we have not grouped our batches. We've left it at none. Okay, instead of grouping by the wait label, because that's the only label I have right now to group by, I'm going to assign another label in addition to our wait label. Let's get something that's simple. How about size? And then let's use a by percentage option. And let's say we have 2 sizes, small and large, and a 50-50 split on them. 50% of the time, and let's use a text. I think it'll be more understandable what we're doing. Let's call this small, and 50% of the time it's large. Now this isn't going to be tied to the weight at all. This is more maybe volume because I haven't set it up to define a small large based on their weight label. Totally new label called size, and it will have the value of small or large. Then on the batch activity in the group by, I'm going to group by a token label called size, token.size. Okay, easiest way to explain this is to run it and just show you what it looks like. Okay, on the batch activity itself, you'll see a description of which batches are being built at any given time. And the shaded area will be the name of the value of the label, small or large, and then in parentheses, the quantity that have been collected so far out of 4. Our batch quantity is 4 and our quantifier is number of tokens. So that's pretty neat, the way the batch activity can create batches according to some group that you specify, typically using a label. Alright, that's all I wanted to show you about the batch activity. Let's move on. Now it's your turn to try creating and executing a customized task sequence using a process flow. The description of this model is simple. An operator is responsible for transporting flow items from a queue to a labeler, which is represented with a processor object, and then must perform the labeler setup time, which takes 2 seconds. After every 15th flow item is processed by this labeler, the operator needs to retrieve a new roll of labels, represented in the model by a cylinder flow item, from a storage location, that's any object of your choice, bring it to the labeler, and replace the empty roll with the new roll. It takes this number of seconds, represented by the triangular distribution, to reload the labeler with the new label roll. And then you can destroy that flow item that represents the roll when you're done. Some questions is, what is the utilization rate of the operator? And does it matter what kind of object represents the label roll pickup location? The answer to that is no. It just needs to be a location. A spot on the floor where you're going to have your operator walk to, pick up a flow item that you will create with your process flow and put it in that object location, and then carry it over to the processor representing the labeler, spin triangular 5, 15, 10 seconds, and then get rid of the roll. But the processor cannot be accepting a new flow item to be labeled during that time. As for how to model every 15th flow item, I'm hoping you'll be able to figure that out using the batch activity. Okay, it's now time for you to try to build this model on your own. Okay, I'll now demonstrate how to build Model 3. First of all, let's create the layout. It's a simple source queue processor sync model. Connect them up. Click drag. Now we need to drag out an operator. And we'll do center port connections. So S, click drag from the queue to the operator, and processor. Now we're going to also use a queue as the location for where label rolls are stored. Okay, we'll go with all the defaults except for we were asked to do a setup time on this processor of 2 seconds and use an operator for the setup. Center port connection. We'll keep the default 10-second process time as well, but no operator for that. Okay, that completes all the editing we need to do on the 3D object parameters. Now we're going to create a process flow. The process flow will be used to model the operator replacing the label roll. More specifically, the process flow will create a flow item, put it in this queue here, and then create a task sequence, a custom task sequence, that will have the operator travel to pick up and load the roll, and then travel to the labeler, delay for the reload time, and then destroy the flow item that represents the label roll and finish up the task sequence. That's all it needs to do. But remember, we only want to replace the roll after every 15 parts have been processed or labeled at the processor. So we'll also need to count how many parts have been processed at the processor, and to do that we're going to use the batch activity. Alright, well that's a little overview. Let's create the process flow. It's a general process flow. It's going to start off with an event triggered source, and then a batch activity. I'm going to just double click here, bring up my quick library, choose the batch, do it again, and this next activity is going to be a create object activity. Okay, I'm going to drag a line down to the next set of activities which will create our task sequence. Okay, start with this one, the create task sequence. Then I'll have these task sequence activities all be part of a block, so I'll double click here. The next one I want is a travel activity. So that's this one here, and it's going to be a travel to object. Double click again. I need a load activity. It's this one here to load the new role. And then travel to the labeler. A delay is part of our task sequence. This one right here. And then we'll throw in a destroy object. We're done with the label role. And then we can finish our task sequence. And that's this one here. And then I'll drag down to a sync, and that's all this process flow is going to do. But we have to edit the parameters. Okay, let's come up here and click on the source. Here's this exclamation point I can hover over and get the sample tool. I'm going to sample the processor, and I'm going to choose the on entry trigger. Now on the batch, it's going to be 15 for the batch quantity, based on number of tokens. So this source is going to create a token every time a flow item enters the processor. And once 15 have entered, we'll know it's time to replace the roles. Okay, nothing else is needed on here. One token will be released, and we'll deal with that token to do everything else we want to do here, like create our flow item. And the instructions said to create a cylindrical flow item, so we'll change it from box to cylinder here. Quantity is 1, and where do we want to create it? I'll use the sample tool and have it created in this queue. Okay, the create task sequence, we'll go with same priority as everything else. It's going to be assigned to token.task sequence. Assign task executor to token.task executor. All the defaults. Okay, the travel task. We want the task executor to travel to the queue. Oh, I forgot. On the create task sequence, I want to reference the task executor as being the operator. So let me sample the operator. Operator 2. Okay, next, load. We will load token.item. That's how we can refer to the flow item that was created by the create object activity. When it created it, it put a label on the token called token.item. Then we're going to travel back to the processor, delay, and the time we were asked to delay was a triangular distribution with minimum 5, maximum 15, mode of 10. That happens to be the default. Destroy token.item. Finish our task sequence per token.task sequence label. And go into the sync. Okay, let's see how it works. Reset, run. There's the first part to be processed. Second part to be processed. Third part. Let's just go through all these. Get up to the 15th one. And the role is getting replaced. And we're back in action. And that's how you build Model 3. We're now going to move on from talking about task executors to talking about conveyors. Here's some key concepts about conveyors in the software. They can do slug building and merge control. We can create conveyors that will accumulate a slug of items and then release it once the slug is ready. Using this feature in conjunction with the merge controller object and or the process flow tool, we can easily implement sawtooth merges without writing any custom code. Range-based transfer points. Operators in the model can pick up or drop off items from a range of possible transfer points along the conveyor, rather than a single fixed point. making it easier to simulate picking operations. When picking items from a conveyor, operators will automatically predict a proper pickup point along the conveyor based on item speed, operator speed, and distance to travel. We have improved photo eyes. We can build more sophisticated logic into photo eyes, such as programming them to trigger certain events or logic when they are blocked or if they are clear for a specific amount of time. We can also make precise adjustments to the height of the photo eyes and the angle they are pointing on the conveyor, replicating real-life behavior. Decision points and stations can be used to build complex logic into a conveyor system. We can place decision point objects and stations on a conveyor to act as a sensor, processing station, or a communication point for other objects, such as the merge controller. Advanced movement controls. FlexSim's conveyor system has many possible options for controlling how items transfer between conveyors, including the transfer speed, delay time, and pop-up distance. We can also adjust a roller skew angle on a conveyor so that items will accumulate on one side of the conveyor if needed. We can also tilt, translate, and rotate items while they move along the conveyor. Item orientation. We can define any orientation for items on a conveyor. This orientation will automatically persist across multiple sections and will update to match the object's orientation when the item transfers through side transfers. And power and free. FlexSim's conveyor system can simulate power and free systems, including a chain's dog gap. Very powerful. Conveyor model concepts. The conveyor module provides objects that create a platform on which to build conveyor system behavior. Here's a list in the library of conveyor objects. So the decision points and photo eyes establish logic points where merging and routing take place. And transfer points establish where items may physically enter and exit a conveyor system or move within the system from one conveyor to the next. Let's give a brief description of each of the conveyor objects, starting with the straight conveyor. The straight conveyor can simulate conveyor belts or roller conveyors. As its name suggests, this conveyor has a straight shape. This is what it looks like in the model. The icon on the left is what it looks like in the library. The curved conveyor is another object that can simulate conveyor belts or roller conveyors, but unlike the straight conveyor, this conveyor has a curved shape with varying radius settings. Join conveyors acts more like a tool than an object. We use it to create a curved conveyor connecting two existing conveyor sections. Decision points. We can use a decision point to build logic into our conveyor system. Decision points can also be linked to a merge controller to notify the controller when a released slug has cleared designated points in the system. A station is an object we can use to add processing points along the conveyor system. The station works very much like a standard processor object, except that it is placed as a point in the conveyor system instead of as an object outside of the conveyor system. Photo eyes are similar to decision points in that they act as a sensor on the conveyor. However, whereas a decision point will fire on every passing item, photo eyes function according to the time the eye is blocked or cleared, much like real-life photo eyes do. They will only clear if there is a gap between items on the conveyor. You can also define a block and or clear time so the respective trigger will only fire if the photo eye is continuously blocked or cleared for a specific time duration. Motors can be used to control whether the conveyor system's are on or off at a given time. Can also be used to sync dog gaps on a power and free chain loop when simulating a power and free conveyor system. The merge controller is an object that can control how different conveyor lanes merge together. We use the merge controller to define a lane release strategy for the merge. A merge controller is generally only used with slug building conveyors. There are 3 additional conveyor objects we need to be aware of: transfers, entry transfers, and exit transfers. These objects are not available in the FlexSim library, but are automatically created whenever we connect conveyors to conveyors or conveyors to other objects. Whenever we connect a conveyor to another conveyor or to a fixed resource in the 3D model, FlexSim will automatically create a transfer between those objects. So in this graphic here, this source has been connected with an A-click drag connection to this conveyor here. In so doing, it created this entry transfer. Now, the entry transfer starts out as a point location, but in this graphic, it has already been dragged to become a longer section of the conveyor for the item to enter in. And here is an exit transfer, and this is what the conveyor to conveyor transfers look like. So, these are the 3 kinds of conveyor transfer objects described in a little more detail, with the appearance shown on the right. Starting with transfers. Transfers are connections from one conveyor to another. They can affect how an item is transferred between conveyors, especially when merging lanes together. Entry transfers are connections from a non-conveyor object, such as a source or other fixed resource, to a conveyor object. They can affect how an item is transferred onto a conveyor. They are positional and resizable. You can drag them to a new position, they'll stay along the edge of the conveyor, or when you click on it, you'll get resizing arrows that will allow you to resize it if necessary. Exit transfers are connections from a conveyor to a non-conveyor object, such as a sink or other fixed resource. Exit transfers have the ability to send for a transport, a task executor, to pick up items and deliver them to another object. Task executors can pick up items from a particular point on the exit transfer or a range of possible points along an exit transfer. So working with transfer objects. Flow items will enter or exit a conveyor from the place in the conveyor where the entry or exit transfer is positioned. We can move an entry or exit transfer by dragging it to a different position on the conveyor as shown here. Drag along the top or the bottom. We can expand the range of entry and exit transfers if needed by clicking on the transfer object and then dragging one of the expansion arrows as shown down here. This is an exit transfer from a conveyor to a queue. Starts out as a point. If you click on it, you see the expansion arrows. If you drag either one of the expansion arrows, it will increase the size of the transfer range. Exit transfers have the ability to send for a transport, as shown on the right here, or in other words, a task executor. In this case, it's a person, an operator. So exit transfers can send for this transport to pick up items and deliver them to another object. Task executors can pick up items from a particular point on the conveyor or a range of possible points along the conveyor. That requires some physics going on behind the scenes to calculate the speed or the point where the pickup will occur based on the speed of the flow item and the operator. There are a few things about working with conveyor objects that are a little different from standard 3D objects. One key difference is that conveyor objects can have global types, which make it easy to quickly update custom properties and logic on several conveyor objects at once. For the most part, we can create one or more global types for each conveyor object, including transfers. When working with conveyor objects, we need to consider whether it would be more advantageous to apply properties and logic locally to a single object, single conveyor section if you will, or whether it would be more effective to create a global type that then we can quickly apply settings to multiple objects simultaneously. In general, the process for using conveyor object types is as follows. Create a global type. Using the toolbox, we can create a new global type and set its logic or properties and give it a name. Then we set a conveyors type. In Quick Properties or the Objects Properties window, we assign a conveyor object to one of the global types we created. Conveyor object, or same applies for transfer types. We can apply a global transfer type to a transfer. And then, if you need to edit the conveyor type, you can do that later and it'll apply to all the items that were assigned that conveyor type or transfer type. If we want to make a global change that will affect the settings for all the conveyors of one type, we can edit the conveyor type settings in the toolbox. It will then immediately update the default settings for all the conveyors at the same time that are of that type. To unassign a global type to a particular conveyor object and edit only that specific object's properties, then what you do is you change the type setting to custom. And that will break the connection to a global type and allow you to edit just the settings of the local object. Many of the conveyor objects can be added to the model the same way we would add any other object from the FlexSim library. We simply click on the object in the library and drag it into our 3D modeling space. The straight and curved conveyor objects will have a default size if we click and drag them into the model. However, we also have the option to define the length and or radius of the conveyors when we first insert them in our models by first selecting the type of conveyor we want in the library with a single click. Then go to the point in the model where we want the start of the conveyor, click, then move the mouse to the end of the conveyor and click again. And this is being shown in this top left graphic. Select the straight conveyor, which it'll do here in a minute. It keeps repeating. Select the straight conveyor, then come out in the model, click, move your mouse, click again. Simple as that. So this allows you to accurately create a conveyor start and end point wherever you need them. Conveyors have two ends, respectively called the start and the end in FlexSim. Although these two ends are connected, they can be moved, rotated, and resized independently. The start is where flow items enter the conveyor, and the end is where flow items leave the conveyor. We can move or resize a conveyor as a single unit. Or we can move or resize the start and end of a conveyor separately, as shown in these animated GIFs down here. This is repositioning the endpoints of a straight conveyor. On a curved conveyor, The endpoints will change the start angle. Well, the start end will change the starting angle of the conveyor, and the end point will change the sweep angle as shown down here in this graphic. And then in the middle of a curved conveyor, you'll see a little green double arrow. If you click on that and hold down and drag, it'll change the curve radius of that section of curved conveyor. In these two graphics down here, it's showing you how you can raise and lower a conveyor. Either the entire conveyor can be moved up or down by clicking on the conveyor, using your mouse wheel to change the height of the conveyor up or down. Or if you want to have a ramped conveyor, you would click on either the start point or the end point and then roll your mouse wheel up or down. Now all of these things we're changing with our mouse, which is probably the preferred method, can also be changed by typing values into the properties window in specific edit fields associated with those points of a conveyor. There are a couple different ways to connect two conveyors together. One way, as depicted on this animation to the left over here, is to click on a conveyor and drag it close to the edge of another conveyor. When the edges of the two conveyors get close enough, they will snap together. After releasing the mouse button, a transfer object will appear that connects the two conveyors together. This transfer will look like a small square box that overlaps the edges of the two conveyors. The second method, and more common method, as depicted in this center animation, is to use the join conveyors object. Even though the join conveyors object is in the FlexSim library, it actually functions more like a tool than a 3D object. But because the tool creates a new curved conveyor in the process of connecting two existing straight conveyors together, it's considered a library object. It's an extremely useful time-saving tool for getting a large conveyor system model built. The primary way to connect conveyor objects to other objects, as depicted in the animation on the right, is to simply create a port connection. However, unlike connecting normal FlexSim objects to each other, when you make a standard port connection, an A connect, in other words, to or from a conveyor and another FlexSim object, it will create an entry transfer or an exit transfer, which is an in-between object that's associated with a specific point or range on the conveyor. An exit transfer is created when you connect a conveyor to another FlexSim object, and an entry transfer is created when you connect a FlexSim object to a conveyor, as shown in this animation with the source being connected to the conveyor. Okay, conveyor routing using decision points. Decision points can be used as target destinations to send items to, using whatever the shortest path along the conveyor system is to get there. The conveyor system has an automatic route finding mechanism. In other words, the decision point to which you send an item can be anywhere in the conveyor system. As long as the target decision point is reachable from the item's current position, the item will use the shortest route to get there. In this animation here, this upstream decision point, which is right here, has standard output port connections, 1, 2, 3, 4 of them here, to each of these 4 downstream decision points associated with each of these conveyors. so long as that decision point is on this downstream side of the connection point to this top conveyor, the software and the flow item is sent from this decision point to one of these decision points down here. The software will figure out the shortest distance to get there, which is a straight shot over and down. This upstream decision point's trigger is what routes the flow item. We use an on-arrival trigger, as shown here on the right, and choose the option to send item. And there's a couple ways of sending it, either by condition or by case or by label. In this case, it's send item by case, and the case function is a label on the flow item called type. Depending on the value of that type label on the flow item, it will do either case 1, 2, 3, and 4, which is associated with sending to an output port an object connected to output port 1, 2, 3, or 4 of the decision point. Decision points can also be used to restrict access. When more than one conveyor feeds items onto a single conveyor, we call this a merge, and the section of conveyor receiving the items from multiple upstream conveyors is the merging conveyor. To prevent items or boxes from colliding and potentially getting knocked off the conveyor, we may want to use decision points to restrict only one box at a time on the merging section of conveyor. To create this logic, we can use decision points on the feeding conveyors. Like in this animation, we have two feeding conveyors. This is the merging conveyor up top. So we can use decision points on these feeding conveyors that use a pick list option called Acquire Restricted Area on their on-arrival trigger, as shown in this screenshot on the left here. An on-arrival trigger, and the pick option called Enter Restricted Area has been chosen. Using this pick list option, the decision point will request access to the merging conveyor, which is our restricted area, for every arriving flow item. If the requested area is not available, the decision point will hold the flow item until the area becomes available. So a very powerful pick list option that does quite a bit for you, manages quite a bit of logic behind the scenes. So on these two decision points of the two feeding lanes, in their on-arrival trigger, the option Enter Restricted Area has been chosen, and the area owner is defined by an output port connection. Current.outObject1 refers to the object connected to the output port 1 of each of these decision points. And what is output port 1 connected to? Yet another decision point downstream, this one here, at the end of our so-called restricted area. To fully define then the restricted area, we will need to connect the decision points on these feeding conveyors to a decision point added at the end of the merge. On this final decision point, we'll use the pick list option called Release Restricted Area on its on-arrival trigger. So that's what this screenshot is showing. The on-arrival trigger of the decision point that is at the end of the restricted area, and we chose the option Exit Restricted Area. The area owner is this object itself, this decision point, the current decision point. And what this does is send a message to the upstream decision points to release the next flow item in line as a flow item every time a flow item exits the restricted area. Next, the rack object. The rack is a subclass of the storage object. The storage object is a parent class of several objects used to store flow items in a two-dimensional grid of storage locations we call slots in the software. These slots are organized first by bay, then by level, and finally by slot number. The rack specifically defines bays in the X direction and levels in the Z direction. So bays in the X and levels in the Z, going up in the air off the floor. This is all in contrast to another subclass of the storage object called floor storage, which defines a grid of storage locations where bays are X and levels are Y, so it's on the floor. Within each cell, as defined by the bay level, there can be one or more slots. And in the properties of a rack, on the dimensions tab, you set all this up for number of bays, number of levels, number of slots per bay, and what the width of the bay, level, and slot is. So, rack slot assignments. How is that done? Slots can be assigned using the slot assignment strategy field. It's on the storage object tab of the rack properties window. There's a field here called slot assignment strategy. One option is the first slot with space, first available slot. You can do this a number of different ways. Labels can be assigned to slots and matched with labels of flow items, for instance. And to assign labels to slots in the rack, you use the painting tool. So that is found in the library, 3D Object Library. In the warehousing group, it's called Paint Slot Labels. It's a tool for painting label data onto storage object slots. Makes it easy to create different storage locations for different part types. The capacity of a slot is defined by the dimensional size of the flow items compared to the dimensions of the slot. Well, there's a lot more capability of the rack object than we are going to cover in this course, but it'll be good to get a brief introduction to some of the rack's features. To really take advantage of the rack's full capabilities in a realistic warehousing model, we would need to use process flow to manage the storage and retrieval of items to and from the racks in the model. Okay, rack minimum dwell time. It's one of the parameters on the flow tab of the rack object. And although this minimum dwell time field is probably not used so much in a real warehousing project, we will be using it in the next training model so that items stay in the rack for a little bit of time before exiting to the next downstream object in the model. In a more realistic warehousing model, we would typically simulate some kind of a demand that calls for items to be pulled from the rack. But in this next training model, the items will simply be released to leave the rack after spending a minimum dwell time. You can use an expression, a distribution of sorts in the minimum dwell time field, or a constant value. So the total time in the rack will be a combination of the minimum dwell time, the forced time you apply to the item that they must stay in there, plus any extra time where the flow item has to wait for downstream availability, or for maybe an operator to carry them out of the rack, or whatever is in your model that's restricting them leaving immediately. Similar to a process time, it treats time spent in the rack as an abstraction. Okay, Model 4, Conveyors. The purpose is to get familiar with the Conveyor library. As far as the description goes, we're going to use the layout on the following slide for the conveyor system, so let me go over to that. It starts down at the bottom here with the source generating boxes for the conveyor, and then they are diverted onto one of 4 lanes, and then this operator takes the box and puts it in this one level rack here. After a minimum dwell time, the flow item leaves and goes to one of these 2 conveyors. They merge into one conveyor, And then right at the end here, this red thing is a station for a final processing time on the boxes in line on the conveyor, and then they leave to the sink. Okay, let's go back. So use an exponential distribution 0,6.5 for the arrival rate of boxes onto the conveyor. Then assign the items a type label and a color based on D uniform 1 to 4. Route the items to a lane by their type via decision points, and use an operator to place items in the first slot with space option of the rack. We'll have the items dwell in the rack for a minimum of normal 30,5. Then after the minimum dwell time, they'll be released, and we are going to use alternating exit lanes for the items as they leave the rack. To do this, use a send to port option on the rack called round robin. It'll alternate, first one lane, then the next, then the other, back and forth. Okay, then create a restricted area with a capacity of 1 using decision points where the exit lanes merge to keep boxes from colliding in that merge zone on the merging conveyor. We'll use decision points to do that. You've seen how that can be done. Then create a station at the end of the merge lane that delays items for 3 seconds before they are pushed to a sink. Couple challenges here if you want to try them. Can you route items out of the rack such that types 1 and 2 use lane 1 and types 3 and 4 use lane 2? And can you set the rack to place items in the slot that is assigned to the item's type label, matching a type assignment of the slot, which you'd have to paint in? Okay, it's now time for you to try to build this model on your own. Okay, I'll now demonstrate how to build Model 4. We'll begin with a source to create our boxes that will go on our conveyor. Now I'll use the straight conveyor, click and drag it over here and click. And then I'll make the 4 feeder lanes to the rack. This is just a matter of click for where you want the start of the conveyor, and then move your mouse and click for the end. Now I'm going to use the join conveyors object or tool. I need to right click to stop connecting at the end of each of these. So click, and then right click here, and then click on this and click on this. Okay. Now let's make a rack. The standard rack object. I'm going to edit the properties. Dimensions tab. Go with 4 bays, 2 levels, and change the bay width to something that'll extend across all 4 lanes here. Okay, let me make an operator. I'll use the mail operator. And continue on with my straight conveyor sections for the takeaway conveyors out of the rack. And then they will merge into this conveyor here. I'll use the join conveyors tool to connect them. Okay, now let's make a station object at the end of this conveyor. And the sink. Okay, now for the decision points. Put one right here, the beginning, and then one on each of these 4 lanes. Then one on each of these takeaway conveyors, and one here. That's going to be for our restricted zone, restricted area. Okay, time to connect. Connect. Source to the conveyor. Each of these lanes here to the rack. From the rack to each of the takeaway conveyors. And from this final merge conveyor to the sink. Now I want to connect my decision points. That's how I will reference the downstream decision points from this upstream decision point. And same with the restricted area I want to create. I'll use output port connections to reference the decision point. Now I want to move these exit points, exit transfers, and resize them. The reason I'm resizing them is so that the operator can pick up the box anywhere along the edge of that conveyor. And then I want to connect the operator up to each of those exit transfers. Okay. Now on the source, let's start editing some parameters here. Change the scale value of the exponential distribution to 6.5 on this inter-arrival time. And then I'm going to use a trigger to assign my type label and color. I'll use the onCreation trigger. Go into data, set label and color. It's already set up for a label called type. I'll keep that, but I'm going to change it to D uniform 1 to 4. So we'll get 4 values for the type. Now I need to add a trigger to this decision point to decide where to send flow items. I'll use the onArrival trigger and the pick list option to send item. And for the destination, I'll choose output port by item type. So it'll send to an output port number based on the value of the type label of the item. Now the rack. First slot with space, we were told explicitly to use that option. That happens to be the default. And then in the flow tab, I want to say use as a fixed resource, and that gives me the option to define a minimum dwell time. And we're going to use a distribution for that, the normal distribution, mean of 30 and standard deviation of 5. And for the send to port, we were told do it round robin. Okay, now to create a restricted area, we'll add another onArrival trigger to each of these upstream decision points. Use the option under area restriction, enter area, enter a restricted area, and the area owner is the object connected to output port 1. And same thing for this one. onArrival is the trigger, and the option is an area restriction for enter area, and the area owner is also output object 1, which is that downstream decision point right here. It also needs an onArrival trigger, And the option will be the area restriction called exit area. And the area owner is itself, this current object. It's kind of already set up for doing the connections we did there. Okay, for the station, the process time was 3 seconds. Okay. Okay. Now we need to, on each of these exit transfers, say to use the transport, but instead of editing this specific exit transfer, I'm going to create a new exit transfer type and then assign all of them to this type, and just check the box use transport, and it'll use the transport connected to center object 1. And notice in the toolbox it adds a global exit transfer type 1. And now it's just a matter of assigning that exit transfer type 1 to each of these other 3 exit transfers. And I can do that through the quick properties here very easily. Change it from custom, which would be a local edit, to the global exit transfer type 1. Okay, we're done. Let's run the model and see what it looks like. Set run, step it. Here's our first part. Okay, let's watch. Remember, we color coded the types. Red is a type 1, green's type 2, blue's type 3, and yellow's type 4. They are diverting to the appropriate lane based on their item type label. And then the operator carries them. Notice how they pick them up from anywhere on the exit transfer lane, but once they all start compiling at the end, that's hard to see. They're being put in the first available slot on the rack, but let's change that now. Remember the advanced challenge? We'll change it from first slot with space to matching labels, and notice it's already set up to use a type label on the slot and a type label on the flow item. Our flow items already have an item label, but our slots do not, so we're going to use this Paint Slot Labels tool to do that. This pops up telling us how the tool works. We're going to change our label value first in Quick Properties on the right. Start off with the value 1 for the type label, and then paint this first bay, both levels, total of 4 slots, and then change to a 2, which is the green color by default. That can be changed, of course. We'll do item type 3 for all 4 slots in bay 3, and type value of 4 for all 4 slots in bay 4. Okay. Next thing I want to do is on the flow tab of the rack, we had that other advanced challenge to, rather than use round robin, to choose a port by case where item types 1 and 2 use the first conveyor, and item type 3 and 4 use the second conveyor, which is connected to port 2 of this rack. So that's all I need to do for that. And let's see what that looks like. Okay. Now the different types are being put in each of the bays associated with that type that we painted on the rack. And notice in the takeaway conveyors, we're getting reds and greens in the first conveyor and blues and yellows in the second conveyor. No longer is it round robin. Okay, that's the end of Model 4 and the Day 3 training.